Hi everyone! This video is the fourth and final part of the series dedicated to the pricing of defaultable bonds with a reduced form model. We will discuss in this video on the calibration of the model, on potential applications, and we will compare different measures of credit spread. As a reminder, the bond price can be expressed as following in a reduced form framework assuming continuous time and constant risk-free interest rate. In addition to the characteristics of the bond, the time to maturity, the coupon, and the risk-free interest rate, the bond price is depending on the default intensity and the recovery rate in case of default. The credit spread is a compensation for bearing credit risk when purchasing the bond. It is equal to the product of the default intensity and 1 minus the recovery rate. Lambda is the default intensity of the issuer of the bond, a measure of its default risk. It is company specific. 1 minus the recovery rate is the loss given default depending on the seniority of the bond. The default intensity lambda can be expressed directly from the credit spread S and the recovery rate capital R. So we can price the bond as a function of the credit spread and the recovery rate. The Z-spread Z is the spread that needs to be added to the risk-free interest rate to obtain the price of the risky bond. It is the additional compensation asked by investor for taking that risk. The price of the bond can be expressed like this as a function of the Z-spread Z. We compare here the two expressions of the bond price as a function of the credit spread S and as a function of the Z-spread Z. And we see that the two spreads are equal if and only if the recovery rate is equal to 0. We will now analyze the sensitivity of the Z-spread to the default intensity and to the coupon. For that, we need to be able to imply the Z-spread from bond prices. Here is a Python code doing that. We minimize the square difference between the bond price P and the bond price as a function of the Z-spread using the SciPy optimize function minimize. For different values of lambda, all other parameters being fixed, we can price the bond and then estimate the corresponding Z-spread. We are doing that with two levels of recovery rate, one at 0% and one at 40%. We see that the Z-spread is equal to the default intensity lambda and to the credit spread S when the recovery rate is equal to 0. When the recovery rate is not null, we see that the Z-spread is below the credit spread S. This is to compensate for the additional cash flow as there is no assumption of recovery rate when calculating the Z-spread. Here is a Python code doing that. The credit spread S is a product of two variables, the default intensity, which is issuer specific, and 1 minus the recovery rate, which is depending on the seniority of the bond. So the credit spread is independent of the coupon of the bond. This is not true for the Z-spread. With this Python code, we calculate the Z-spread of the bond for different values of the coupon. We see that the Z-spread increases with the coupon. It makes sense as a higher coupon means a higher proportion of the coupon and a lower proportion of the recovery rate in case of default in the cash flows of the bond. There are three parameters to be calibrated in our pricing model: the risk-free interest rate R, the recovery rate capital R, and the default intensity lambda. The risk-free interest rate can be estimated from treasury bonds with similar tenor than the bond. The recovery rate is depending on corporate bond seniority. The higher the seniority of the bond, the higher the expected recovery. Numbers here tends to be market convention in line with historical average recovery rates. The recovery rate of a senior unsecured bond will be typically 40% on average. Knowing the recovery rate, the default intensity can be estimated from bonds of a similar issuer but with different maturities, seniorities and coupons by matching the bond prices. In this illustration, we see that there is a term structure for the default intensity, which is a function of the tenor, with a higher default intensity for a higher tenor. We can fit the curve with a parametric model using, for example, a Nelson-Ziegel function, which is popular in fixed income. More advanced models, assuming non-constant risk-free interest rates and default intensity, can be used to take into account the whole term structure of the curves in the pricing of the instruments. Classical bootstrapping and interpolation methods can be used to calibrate the discount factor. while the survival probability function can be estimated assuming a non-constant default intensity, deterministic or stochastic. I will not go more into details on these advanced models here. There are not always enough information from bonds on one single issuer, not enough bonds or tenors to well calibrate the term structure. When this is the case, additional information from bonds from other issuers or other markets such as credit default swap may be required. Here are several potential applications of the pricing model. It can be used for the pricing of a new issuance, for the pricing of more complex bonds such as hybrids or contingent capital bonds, or more complex products, derivatives, structured products. It can be used for relative value analysis between bonds of a same issuer, bonds of different issuers, or bonds versus CDS of a same company, for example. It can be used as well for risk management purposes. Thank you for your time.